So first, I want to thank you for giving me an opportunity to speak at this venue again. When I come to OpenSearchCon, it feels like I'm coming back home every time, and especially an opportunity to stand up here and tell you about what we're doing here every year, so we can all catch up, but more importantly, we can all work together to see what the future looks like. So for those of you that don't know me, I'm Mehul Shah. I'm the CEO of Aryn AI, an AI company. And we're living in exciting times, especially for people like me, who are trying to solve problems with unstructured data, or unstructured data problems in the enterprises. Generative AI and LLMs are basically radically transforming what we can do now, okay? And by the end of this talk, I hope to convince you that there's so much more possible than pure search with LLMs. And at Aryn, what we're building is a new class of systems for deep analytics, or the buzzword these days is agentic. So you can see I changed the title to add agentic there. Analytics that marries a combination of techniques from search, databases with LLMs to help many enterprise customers. Okay, so just a little bit about us. Our goal, our mantra is to try to make it easy for enterprises to use generative AI models, sort of modern AI models, for unstructured data analysis. And particularly, we strive to give these enterprises accurate, reliable results at scale. We're a founding team from AWS, Google, and Meta. We've been building cloud and data and AI systems for decades. We are proud members of the OpenSearch Software Foundation. We're one of the founding members. We have a couple of committers onto the OpenSearch project. They're part of the technical steering committee. I'm part of the governing board. As I said, this feels like home. And finally, we've been funded by some top-tier investors, 8VC and Factory, and so we're going to be around for a while doing this. Okay. And in this audience, I don't think you really need this introduction, but I'll go over it with you anyway. You guys know that 90% of enterprise data is unstructured, and there's a gold mine of untapped information in there. And for the last 30 years or so, the most effective tool, and it's been a pretty effective tool, has been search for giving enterprises insights from that data. But more recently, over the past 3 to 5 years, we have these new systems, these generative AI systems, that are giving state-of-the-art results without having an in-house search team or an AI team, okay, on unstructured data. So they allow you to do a variety of things like summarization, entity extraction, sentiment analysis. These are incredibly powerful tools. But more importantly, they're getting better and better at a dramatic pace. Okay? They're getting faster in terms of their inference speed by almost 10x per year. This is insane. Okay? Even more insane is for any particular class of model. For example, this graph shows you the price for a GPT-4 class model. Over the last year and a half, it's dropped nearly 100x. Okay? So these are also getting much and much cheaper. And so far, what have we figured out how to do? We've figured out how to take an LLM and stick it at the end of our pipelines. And this is actually a pretty reasonable approach, at least in the last 2 to 3 years. Okay? Why? Well, LLMs are much more expensive than running your search. And you wouldn't really want to do it in line. You would really basically want to do it when you have a small amount of results that are coming back, and then you allow the user to kind of interact with those results. And this technique, known as retrieval augmented generation, or RAG, there are variations of this technique that people are using all over the industry now. But I want to offer you a different perspective on this technique. Okay? And the perspective is that instead of thinking about this as an LLM being stuck at the end of a pipeline, think of an LLM as the new compute platform. Okay? It's the basis on which you're actually building your applications. It's not an add-on. It's not something that you're sticking to the side, but it's something that you're actually going to be building your systems on. Okay? And the context that it has is basically the new way of thinking about main memory. Okay? So if you think about RAG in this particular framework, or from this particular perspective, what RAG applications are really doing is basically they're using search as a way of retrieving the most relevant results, top K results, putting it into memory, and then computing over them. And this approach makes it really easy for people to ask natural language questions, have a natural language interface over their data, but the answers that they're getting are limited by the context that you have in your LLM, because that's basically the architecture that you set up. And the question we have, and we asked our enterprise customers, is this enough, or do we need more? And the short of it is enterprises want to do a lot more with their unstructured data that goes well beyond question answering. Okay? And here's some sort of 3 example use cases that really are looking at enterprises that are doing sort of, looking at people in enterprises, knowledge workers in enterprises that are doing deep research effectively over the underlying data that they have. Okay? So if you're looking at financial services companies, you're looking at pharmaceuticals, you're looking at a securities regulator, they all have analysts. And these analysts, part of their job is to look at collections of data that typically have a common semantic schema, right? So for example, you might be looking at earnings calls and filings if you're an investment company. Or you might be looking at, if you're in a marketing organization of a pharmaceutical company, you might be looking at interview transcripts with doctors and insurers. Or if you're in a securities regulator, you're looking at legal filings, judgments, and memos. And what you want to do is you want to look for patterns. A lot of these analysts are looking for patterns that span across their data collections. An example is summarizing the yearly revenue growth and outlook of companies whose CEO has recently changed. The answer isn't in a single document. Okay? The answer is really computed by looking across all your documents and synthesizing a result. Provide the top reasons PCPs prescribe medication X, where X can be any medication versus specialists. Again, looking across your interviews and trying to gather that information and to synthesize a result. And so going beyond just simple retrieval augmented generation, we have sort of a broad class of patterns that we're calling deep analytics. Okay? And RAG is sort of a subset of those types of patterns where what you're doing is hunting and pecking for information. Now, hunting and pecking and answering a question is still fairly hard. Finding the right piece of information, understanding the layout of your documents, and figuring out where the information is, and then putting it back together, a non-trivial task. But that is just one pattern. Okay? So what was the capital expenditure for Google in Q4 2024? Right? Usually there isn't a single line item. You have to know how to compute the capital expenditure. On the other hand, the other kinds of questions and analysis that people are doing are much more of a sweep and harvest type pattern. From all the board decks that I have and investment memos that I have, summarize the capital outlays of top companies by ARR in the construction engineering market. So you're going to have to sweep through your data. You're going to extract information like ARR and what market those companies are in. You might have to filter on construction engineering companies, sort by the ARR, summarize the results, and then finally give you an answer. So this isn't the typical RAG style pattern that you would see based on search. Or it's more like an analytics type pattern. Or you might want to think about bringing multiple data sets together. And so there's sort of a integrate and synthesize style pattern that we see our enterprise customers asking for. Okay? And so what we're doing is building a new category of AI data systems. We're calling it agentic document intelligence. Okay? It allows you to do transformation, ad hoc analytics over your data sets, as well as reporting. And it's actually been in public preview for a couple of months. Okay? So if you want to go and check it out, you can go to our website, click on that QR code, and you can try it out yourself. Right? So what does the Aryn platform look like? Well, it's got sort of a few main components. The first thing that we have is a parsing stack. We call it docparse, that takes your underlying documents and extracts the underlying sort of constituent components of those documents, images, tables, graphs, figures, paragraphs, section headers, and so on, and then indexes all of this stuff in OpenSearch. Okay? And this is why we're here at the OpenSearch conference. OpenSearch is a great platform which has a whole bunch of features and functionality that have been put together over the last 15 to 20 years that we can all leverage. Okay? So we use OpenStore for our indexing. We use reverse indexes. We use the metadata indexes, the vector indexes, and so on. And then for doing all of the extraction and sort of the transformations after the extraction, as well as sort of enrichment and metadata extraction, we're using a platform that we've built called Sycamore. Okay, it's open source, it's Apache v2 license. You can check it out yourself. And finally, we have a deep analytics agent that uses all of this information and uses reasoning on this complex data that we've created to come up with plans to answer and search and give you analyses for the tasks that you have at hand. Okay, so let's actually see it in action. All right, so this is what our system looks like. If you actually sign up and start using the system, at the core of the Aryn platform is the notion of a central data structure that we call a document set. It's kind of like a table, but instead of having rows in a table, what you have is documents. And what I have done here is loaded a whole bunch of different documents from the NTSB on airline incidents or airplane crashes in a couple of months in 2024. Okay, let's go to a particular one that's actually quite interesting here. It has a whole bunch of different elements in the document that's there. So in this particular accident that happened in, I believe, Tennille, Georgia, you'll see that there are tables, images at the top, tables underneath, narrative that actually describes the analysis, images that actually show you what actually happened. The connecting rod on the landing gear apparently was missing and caused the crash, and so on and so forth. The first thing that our system does is actually parses all of this information, breaks this information down into its constituent components. So images, tables, text, section headers, and so on. Okay, and then after it's done this segmentation, we also send the particular piece of information to the appropriate model to extract the underlying text or the underlying structure. So for example, for tables, we have our own table models that'll actually get down to the individual cell levels and deal with spanning cells and spanning rows and so on. And it's really about pulling this information out and making it accessible, which gives us the high accuracy and the quality that our customers are expecting. Okay. We also use VLMs behind the scenes to summarize images. So in this particular case, here's the image, and here's the sort of English description of that image. We take all of this stuff, we chunk it, we put it in OpenSearch. Okay. We also allow you to extract a bunch of properties. Now the LLMs in our system can recommend properties to extract from your documents. So this is basically a schema for all the documents that you have, where there are sort of common things that occur across those documents. In this case, we pulled out things like location, date, time, things that are actually in the table at the top, but also other things like wind speed, temperature, wind direction, which you'll really only find in the analysis and the pros. Okay? You can actually add your own fields here, modify the description of certain fields in case you want different things in here. But what we've found is to get good quality answers, you need a combination of both chunking and vector retrieval, as well as key metadata, these key properties that help you navigate very large document collections. Okay. So now let's see it in action. Let's imagine we want to ask some questions over this stuff. All right, so we have a deep analytics agent over here. You ask a question, and the first thing that it's going to do, here's a very simple question: what incidents occurred in July 2024 involving birds? What you saw it do, if you didn't see it, I'm going to kind of zoom in a little bit here, is it actually used the model underneath to come up with the plan. It actually reasons about the question. It has a bunch of information about the properties on the right that you've pulled out, and decides whether to use the properties, whether to use vector search or hybrid search or semantic search, and comes up with a plan to actually answer the question. In this case, because it noticed that it was July 2024 and we have date time information, we're going to use that instead of a vector search. It's going to be much more precise to be able to actually pull the documents that you have out. And then it's going to use a filter, so an operation where you actually take every document after all of the information from it has been pulled out into text, and sends that information to an LLM on the fly during the query to filter for incidents that involve birds. So let's run this plan. Okay. And if I run this using just simple semantic search, you're going to get a whole bunch of sort of false positives, false negatives, and things you're going to miss, basically. And it's going to be up to the user to kind of search through the top K results to figure out whether they've gotten everything here. In this case, I'll show you the steps again. It retrieved 36 documents, that had 36 incidents that happened in July, filtered to them, and there were only 2 that involved birds. Let's open up one of them. Okay, and you'll see that there was an airplane impact with the bird resulting in substantial damage to the right wing. So pretty cool, right? It got the 2 exact answers that we were looking for. Let's ask a little bit more sophisticated question here, which is, list all the incidents that happened in the Midwest. Okay, now, who considers over here, raise your hand, Texas as a Midwest state, right? All right. Who considers, raise your hand over here, Missouri as a Midwest state? Okay. Exactly. So nobody really knows, what we mean by the Midwest. And if it's going to do a KNN search, right, like it's showing over here, I don't actually know what I'm going to get out of this. So I'm going to be a little bit more precise. So in our system, if you don't like the plan that it comes up with, you can actually edit the plan, right? You can ask it and you can just give it a narrative. You can say, hey, please enumerate the Midwest states and use an open search filter. Now, hopefully, if the demo spirits are, on my side today, it's going to rewrite that plan and it's going to enumerate all the various states that it thinks actually happen in the Midwest and use an open search filter for it. So just give it a second. Oh, it's still doing a thing. Let's try it one more time. Please enumerate this worked this morning. Try it again. It's not going to behave with me today. Let's cancel the query. Let's try it one more time. Oh, there we go. Enumerate the incidents that occurred in the Midwest. Okay, let's try it one more time. All right, so now it's doing a full database clan, okay? Please enumerate the states and use a match filter. And if it doesn't work, I'm just going to run it anyway and see what happens here. Here we go. We use the match filter here to enumerate the states. Okay, so it turns out that Missouri is in this list, North Dakota is there, South Dakota, Wisconsin's there, but Texas isn't. So now let's please add Texas into the list of Midwest states. All right, now let's run the plan, okay? So now I know exactly what I'm gonna get, okay? I know exactly what the plan is. I know exactly how it's actually evaluating all of these things. Turns out there were no incidents that actually occurred in those states. All right, let's ask a different question. Please list all the incidents that occurred in Florida. All right, so it decides to use a match phrase. Let's run this. Okay, how many documents are we going to get back? So it turns out that it's about 10.10. No, more than that. How many incidents do we get? 10, 11, yep. 10 docs that occurred in Florida. Okay, let's actually save these things in a bookmark. So let's call these Florida incidents. All right. Now, what we've done by kind of saving it in a bookmark is now we can use that as a source from which we can do additional analysis. So now looking at the Florida incidents, please list the incidents that involved Piper aircraft. And in this particular case, instead of going over the entire document set, you're only going to be going over the Florida incidents, and you're going to be looking for incidents where the aircraft includes Piper as the model there. So here are the two that you see over here. Let's do one more. What were the most commonly damaged parts and incidents involved in Texas? And you can see that the system actually comes up with a dramatically much more complicated plan, because what it's doing is it's actually pulling out information from the underlying document as it's actually coming back to you, because the particular damaged part information is in the narrative text, okay? And it's not in any of the fields that we've created ahead of time. So it's going to go and get all the documents related to Texas. It's going to use an LLM filter to make sure that it actually includes Texas in there. Now, obviously, there's multiple ways of doing this, but this is one possible way of doing it. It's going to extract the damaged parts on the fly, split all of these damaged parts into their separate rows, do some grouping, and then give you a result. So let's go run this thing. Okay. Now, you can see that you can get arbitrarily complex plans here. You can actually compose these plans using bookmarks, and we can kind of go over this over and over again. But you'll see over here, for example, that the right wing damage in these documents occurred twice, fuselage twice, left wing once, and so on and so forth. And if you wanted to figure out, okay, what incidents actually had those damaged parts in them, in addition to basically giving you the output, what we do is we show you the sort of intermediate results along the way. So in this case, here are all the incidents that occurred in Texas. Here are all the damaged parts that were pulled out, okay, in this particular column. We can go to the next step over here where we took all of the entries. Here are the damaged parts, okay, and what we did is we basically unrolled them. So the propeller and the nose landing gear actually occurred in a single incident, but we unrolled them, and then we could do grouping and then summarization and so on and so forth. So this is what we mean by a combination of database operators as well as LLM-based operators. So you can try a whole bunch of different things. Go and sign up, put in your documents, and try this out and see if the planning works for you. And if not, try rewriting the queries. We're using LLMs behind the scenes, and your accuracy is going to depend on how well the LLM can actually do the planning. Okay. All right, let's go back to the presentation. All right, so let's dive deep and hang on. See how we actually made all this stuff happen, okay? So the key challenges in making all this work is first, you've got to figure out how to parse all these unstructured documents. Then you need some way of creating these ETL pipelines to enrich and extract the fields and the properties from the underlying data and index all of this information. And then you need a way to convert all of these natural language tasks that I was issuing into execution plans that you can then run at scale, okay, and make them easy to verify. So the first thing is that we have this thing called doc parse. It's not a single model there. It's actually a collection of multiple models that we orchestrate, okay, to get you some high quality extraction. We have our own model for segmenting these documents. We take all the documents and we literally print them. We create an image out of all of your PDFs, all of your Word documents. We handle 33 different types of documents, and we literally create an image. And then we have a bunch of image models that will then process those images. We have one for segmenting. We have another model for extracting text from text-based elements that are there. We have another vision language model. Sometimes we use some of the large vendors' LLMs for extracting information from the images themselves, like the summaries. We've built our own table extraction model that does a very good job of getting down to the cell level. And then we do a whole bunch of post-processing to kind of clean up the output and arrange it so that you can then get it into Markdown format, HTML format, or the various chunks that you need to be able to index all of this stuff. Why did we do all of this? For two reasons. One, better accuracy, right? If you take all the other sort of hyperscalers, some of the popular open source or leading startup companies out there, and you compare us to our Aryn doc parse with those other other products, we're somewhere between 1.5 to 2.5 times better in terms of segmentation, end to end, in terms of being able to actually give you accurate answers, to get to 97% accuracy on a customer support assistant. And what we've learned with these enterprise use cases is you really need to be in the high 90s, okay, to make this useful for your knowledge workers. And for the customer support assistant, we basically nailed it. For Finance Bench, which is an open benchmark, about the best that you can really do is 78, 79%, and we're pretty much there, okay? All right, so now let's talk a little about Sycamore. What is Sycamore? It's an agentic data flow system. Why do I call it agentic? Because what it does is it allows you to run these operators, like you saw, for both ETL as well as query processing. And instead of trying to stuff all your documents and stuff all the information that you have into the context and asking the LLM to do some really complex analysis, which it may or may not be able to do, what we're doing is actually breaking down the problem into some smaller sub-problems, okay? And then for each of the problems, focusing on that one particular thing that you have to do really well, like extracting information, filtering, and so on. And that's what gives you the higher accuracy. Developers write the Sycamore pipelines using Spark-like Python programs. Okay, it's basically dotted notation, transforms, and you'll be able to see an example of this in a second. And all of this is open source, so you can download it from GitHub and try it out yourself. Okay. What is the document model in Sycamore? Well, it's basically a tree-structured document model. They're represented as trees. Each node in the tree has arbitrary properties that you can associate with them. And the leaves of the tree are the elements that correspond to the pieces of the document that we pull out. And we group all of these documents into docsets. Docsets are distributed collections. They're analogous to data frames in Spark. So we really like the declarative model that Spark has, and that's how we actually build our pipelines, as opposed to sort of the procedural models that other people have built. In Sycamore, we have a variety of different operators, both structured operators that you would find in database systems, things like retrieving stuff from a database, mapping, filtering, group by, aggregation. And then we have the analogous semantic operators that are associated with the structured operators. Things like querying vector database, where there's some fuzziness to what comes back, using an LLM filter, using an LLM for extraction. You can actually even use LLMs for grouping and summarizing and so on and so forth. You saw some of those operators when we were doing the more complex breakdowns of the incidents that happened in Texas, for example. Here's what a Sycamore script looks like. Okay, Sycamore script at the top, you have to kind of, here's an example that shows you how you can extract a whole bunch of properties from your underlying documents using a Sycamore script. You first specify a schema. You have some key, the property names. We support a bunch of different types, strings, booleans, numbers, and so on. We also allow you to provide a little description of the particular property there. And that description actually goes into the prompt to be able to accurately pull that information out. You're going to the next set of lines here are basically specifying which model to use and which operator to use to do the extraction. In this case, we're using OpenAI to extract the fields for each document. And you'll see that we're looking at basically a path, either in S3 or in your local file system, using doc parse to actually segment the information, and then actually calling the extractor. And then finally at the end, this script basically takes all that information, explodes it. An explode operator is basically taking taking the individual pieces and flattening them, and then running them through an embedding model so then you can index it. Okay. All right, so now how do you do the query planning? Well, we have yet another component in our system that we call Luna. It's the query planner. It takes a natural language query, turns it into a logical plan, okay? And then from that logical plan, there's sort of an intermediate representation there. We then turn it into a physical plan using basically these Sycamore operators and the Sycamore scripting system that we have, okay? And what we learned from the Spark world is that whether you want to do ETL or you want to do analytics, you can use basically the same set of operators to do both, okay? All right, so now how do you actually get the Luna planner to actually plan the appropriate queries? Well, it's actually relatively straightforward. We have a preamble, kind of describes how to do this. You have to give it a schema. You tell it the operators that are available. You give it some examples and some sample questions and some sample query plans. And it does remarkably well in terms of being able to go and solve those problems. Now, we can also use RL to refine how well this planner works. So as you see bad plans, you can actually say, this is a bad plan. You should actually create a plan like this. It'll update the various prompts, and now the next set of plans will actually come out to be much better. And so this is some of the stuff that we're working on internally in the team to get you even more accurate results. So here's a simple sample query plan. This is the one where we were looking for incidents in Texas and extracting damaged parts and doing grouping and counting and so on. We ran a very simple benchmark. We came up with about 30 questions on about 100 NTSB incident reports, the same kind of reports that we showed you over here. And we didn't do anything other than just basically run with the planner that we have without doing any RL, any kind of fine tuning. We just basically ran about the sample questions, and just out of the box, we got 20 out of 30 right in terms of the right plans as well as the right answers. Now, there were a whole bunch of errors that we found that could be easily fixed by just rewriting the plans. And rewriting the plans not by actually doing anything finicky, but just asking it to use a slightly different operator with a little bit of human feedback. Okay? And so this leads me to sort of the last part of my talk, which is how is this stuff going to actually get used in production? It turns out that with any LLM or generative AI-based system, explainability and iteration, especially when we're talking about deep research or deep analytics, is going to be essential. Okay? And the analogy I like to make is with coding systems. Okay? Terence Tao said this. He's like, AI are incredible guessing machines. They do a phenomenal job of trying to guess the right answer, but they can be wrong. And the only way to make sure that they're right is to independently verify their output. And with coding systems, this is sort of the natural flow, right? And how people work with these systems. You generate some code, humans look at that code, or they have some tests that are actually going to test that code. There's a dev pipeline, there's a production pipeline, and then you deal with bugs, and then you kind of rinse and repeat. But when you're doing analytics, and you ask a question like number of planes that crashed in the Mojave, and you get 21 back, how do you know that it's right? Well, you need to be able to inspect the plans. You need to have the ability to be able to know what the system did, look at what the answers were, follow up, and ask different questions in different ways to kind of build trust with the system. And that's what we've done here. Okay? So getting the human out of the loop is not the point. The point here is to make the human much, much more efficient with the documents that they have. Okay? So to conclude, I hope I've convinced you that Gen AI unlocks a lot more of the batch AI use cases that were out there before. And users want to do and can do now because of the improvements in AI systems, their speed, cost, performance, accuracy, much more than just simply putting the LLM at the end of your pipeline. I think you can put it at the beginning of your pipeline, in the middle of your queries. You can kind of sprinkle them everywhere. Deep analytics is an approach where we use agentic reasoning with a mix of database-styled structured and semantic operations from LLMs. And there's a lot more room here that we can, for optimizations and improvements. You saw some of them today, right? And then finally, verifiability is critical. We've just scratched the surface here, okay? And human in the loop is absolutely needed, and there's much more room for explainability, but we've got a great place where people can start. So with that, I want to thank you for listening, and I'll take some questions. Go ahead.
Great stuff. I love it. But it seems like you take it one step further. Instead of talking about verifiability, why isn't the system aware of the ambiguities and saying, hey, I've seen more than one definition of Midwest, and I've been using this one. Or, hey, Mojave Desert is actually a very ill-defined space. I'm using this definition, which doesn't matter because, in fact, there's nothing within 20 miles of that, outside of that area that you care about. You know, whatever. Why aren't we using that sort of intelligence to help find the problems?
Yeah, I think, so to repeat the question, there's a lot of implicit information that comes in with a session with a user. Implicit information like, what they mean by the Mojave Desert and its nearby, locations, or what they mean by the Midwest states, and why are we not using, that information? I think the short answer is we would love to, we just have to get there, okay? There's a lot of context that gets built up in an interaction, and exactly how and when to use that context, what to pull from to be able to go and actually put in to the LLM so that you can do proper planning is an open area for investigation and research right now. We're just getting started, so I think it's a great suggestion.
Yeah, I guess I was the agentic seems fantastic, and then you say, oh, the way you debug it is by looking at the query it produces. So wait a second, you've taken this very high-level tool, and now you're asking me to debug the query. That seems like you're throwing it back.
No, I apologize if I said that this is how you debug the query. What I'm trying to say is that you need a way of building up trust, okay? And so the way you build up trust is, you see a system that, repeatedly kind of gives you solid answers, answers that match your intuition, as well as answers that are consistent depending on how you ask the question 4 or 5 different ways. And when you see some kind of conflict and disagreement, you use the verifiability mechanisms that you have to figure out and resolve where that's coming from, okay? So I guess that would be debugging when that happens. But ultimately, all of these systems are fallible, and you need some way of basically building up that trust. So I'm not suggesting that you should be debugging every query, okay? What I'm suggesting, though, is when there is doubt, you need a way to figure out what the heck happened. Okay.
Thanks.
Go ahead.
Yeah, so I just have a question on the query planner. So I'm just thinking if the query planner is intelligent enough to choose the right search type based upon the query. For example, in your example that you showed me, like Texas, that's the first query it does based using vector search. So where keyword search would be even more better for
yeah.
So does it do it intelligently using the right search type? If it does that, how is it going?
Yeah, so the question is, there are a lot of different ways for getting the right answer for a particular query. And in the example that I gave, there were 2 different ways that we filtered for Texas. One was by basically doing a filter on the location. Another one was by doing a vector search and then using an LLM filter afterwards, which was probably just as accurate as the first one, but much slower, right? And what we have done is when we, the kinds of things that we want to explore are looking at ways of taking a plan and then rewriting that plan based on simple rules, okay? 1 more minute left. Rewriting that plan based on simple rules so that you can get the best the best approach for that one particular subplan. Now the challenge here is that if you have sort of vector-based and LLM-based operations, you have to be very careful that you don't remove the fuzziness that the user wanted. Or vice versa, if you have a bunch of plans where there are structured operations, you have to be very careful when you move to semantic operations that you don't introduce additional fuzziness that are there. But there are simple rewrite rules here that'll help you kind of get some solid plans. That said, the only way that that you're doing well is coming up with the benchmark, coming up with a benchmark not just for here are the right answers, which is what most people have been doing, but also coming up with a benchmark for here are a bunch of queries and here are some legitimate queries and their query plans that you should be coming up with to come up with the right answer. So having a benchmark for the intermediate results as well. Okay. Last question, and then we'll, yeah.
So I'm going from the stack from the back end all the way over to the front. Even without the Gen AI in the front, your rich set of operators and the human interaction, this seems to be a very accurately usable tool. What features does the Aryn Gen AI unlocks in this tool? Just beyond the natural language capabilities, is there any other use case that you see adding the Gen AI in the front?
That's right. So the question is, hey, Gen AI is quite useful. So are all of the pipelining tools that you have. They're also useful. Can you tell me what Gen AI does in addition to all of the pipelining stuff that you have? Is that the question? I want to make sure that I've gotten the right answer.
Do you see a potential that it unlocks that Gen AI has to be?
Yeah. So the thing that the generative AI systems do for you in the sort of query planning and ETL part is you can answer questions that you couldn't answer before. Right? So all these structured operators just didn't have a level of fuzziness that you needed. For example, landing gear and float. A float is a landing gear for planes that land in the plane. These LLMs have that implicitly kind of built into them, and so they can create those groups and those filters that kind of automatically match those things without having to build your own individual models around it. So adding LLMs into the actual pipelining, both on the ingestion side as well as on the query side, gives you this ability to reason on the fly that you couldn't do before. Okay. Then there's a separate set of things that we do with LLMs, which is all the planning to actually create the plans, as well as the interaction with the user. That is actually useful for two reasons. The planning is useful because if you take a task and you break it down into smaller pieces, it brings up the accuracy of the answer. Otherwise, you just end up with a bunch of stuff that you stuff in the context, you hope that it does the right thing, and you have no idea if it's right or wrong. The interface to the system also now makes it accessible to more people. Right? So developers, for example, are really used to building Langflow chains. Great, awesome, but if you're not a developer, what do you do? And so we were talking to analysts who were like, I'm never touching this stuff. Well, okay, then don't touch it. Just take a look at the answers and see if you got it right. Okay? Some of them were like, hey, no, I want to see the plans. So it opens up the system and makes it much more accessible to folks who are quite sharp at what they do, but they're not technical in the sense that they understand how these systems are built and used. Okay? Okay. All right, thank you folks for listening and wonderful questions. I'm happy to talk offline. That's it.